Hi, so let's solve question number 1. Explain the meaning of differentiation and what are the techniques of differentiation. So, meaning of differentiation is a way to find how fast something is changing. It tells us the slope or rate of change of a function at any point. For example, it helps us find speed from distance or growth from time. So next, these are the techniques and example of differentiation. Number 1, power rule. Number 2, constant rule. Number 3, constant multiple rule. Number 4, sum or difference rule. Number 5, product rule. Number 6, quotient rule. Number 7, chain rule. Number 8, implicit differentiation. And lastly, logarithmic differentiation. So let's move to the calculation part.
Hi, so now let's solve questions 2. For questions 2a, we are given the function which is y equals to 3x squared secant of x plus 2. Since this is a product of two functions, we will use the product rule, which is dy over dx equals to u v prime plus with vu prime. So for this question, we will let u equals to 3x squared, so the u prime will be 6x. Then we let v equals to secant of x plus 2, so the v prime will be secant of x plus 2 times with tangent of x plus 2. Next step, we will apply this into the product rule. So it will be dy over dx equals to 3x squared times with secant of x plus 2 times tangent of x plus 2 plus secant of x plus 2 times with 6x. So next we will expand the bracket and we will have 3x squared secant of x plus 2 tangent of x plus 2 plus 6x secant of x plus 2. Last but not least, we can factor out the secant of x plus 2. So our final answer will be secant of x plus 2 times with 3x squared tangent of x plus 2 plus 6x. So next, let's solve questions 2b. For questions 2b, given 4x plus 2 over cosine x, so whenever you see one function divided by another, like a numerator over a denominator, you should immediately think of the quotient rule, which is dy over dx equals to vu prime minus uv prime over v squared. So for this question, we will break down our function and let u equals to 4x plus 2, so the u prime will be 4. And then let v equals to cosine x, so v prime will be negative sine x. So next step, we will apply this into the quotient rule, so it will be dy over dx equals to cosine x times 4 minus 4x plus 2 times with negative sine x, and the denominator is cosine x squared. Now we will expand the bracket. Be really careful with the signs here, that negative on negative sine x flips the sign of the second term. So we distribute this sign across both terms in the bracket. So we will have 4 cosine x plus 4x sine x plus 2 sine x. Last but not least, if you notice here, the last two terms share a common factor of sine x. So we can also factor out the sine x in the second and third terms. So the final answer will be 4 cosine x plus open bracket 4x plus 2 close bracket times with sine x over cosine square x. So that's our derivative. Thank you.
Hi, let's solve question 3. Given y ln 3x minus e to the power of 2 plus 1 minus tan 4y equals 0. We need to find dy dx using implicit differentiation. For the first term, we have y multiplied by ln 3x. Since y is a function of x and ln 3x is also a function of x, we are multiplying two functions of x. So here, we must use the product rule to differentiate. In product rule, we say if u equal to y and v equal to ln 3x, then u prime is equal to dy dx because we are differentiating y with respect to x, and v prime equal to 3 plus 3x equal to 1 over x. Since the product rules is uv prime plus vu prime, then the derivative is y over x plus ln 3x dy dx. Now, for e to the power of 2x plus 1, we get 2e to the power of 2x plus 1. For tan for y, the derivative is 4 secant squared 4y times dy by dx. Now, combine all the derivatives. So, we get y over x plus ln 3x times dy by dx minus 2e to the power of 2x plus 1 minus 4 secant squared 4y times dy by dx equals 0. Then, factor out dy dx. So, dy dx open bracket ln 3x minus 4 secant squared 4y close bracket equals to e to the power of 2x plus 1 minus y over x. Then, the last answer is dy dx equals to 2e to the power of 2x plus 1 minus y over x over ln 3x minus 4 secant squared 4y. That's all.
So moving on to the last question, which is question number 4. The question asks us to use linear approximation to estimate the value of the fourth root of 80.99 minus 2 divided by the square root of 80.99 and correct the answer to 3 decimal places. So first, let's define and simplify the fx, which become fx equal to x to the power of 1 over 4 minus 2x to the power of negative 1/2. And after we simplify the fx, we can find the derivative of fx, which is f prime x equal to 1 over 4x to the power of 3/4 plus 1 over x to the power of 3 over 2. And now we can apply the linear approximation formula, which is fa plus f prime a times x minus a. So here we have x, which is the given value, equal to 80.99, and then we have a, which is the chosen value or initial value, equal to 81, and x minus a equal to negative 0.01. And now, with all the information we get earlier, we can substitute and compute them using the formula of linear approximation. For the fa, which is the fourth root of 81 minus 2 divided by the square root of 81 equals to 25 over 9. And for the f prime a, which have 1 over 4 times 81 to the power of 3/4 plus 1 over 81 to the power of 3 over 2 equal to 31 over 2,916. And now we can calculate everything, which 25 over 9 plus 31 over 2,916 and time negative 0.01. Therefore, using linear approximation, the value of the fourth root of 80.99 minus 2 over square root of 80.99 is approximately 2.778.
So, from these topics of techniques of differentiation, we've covered the product rule, power rule, quotient rule, and chain rule. So, we can conclude that this technique helps us to find derivative of different types of functions, and this technique also helps us to find complex functions quicker and more accurate. And lastly, mastering this technique is important to solving a real-world problem in mathematics, science, and engineering. So in short, techniques of differentiation help us to find derivative efficiently and making calculus more practical and powerful. So that's all from us. Thank you.